Let us continue with the constraint satisfaction problem. Another type of CSP is flexible CSP. We have seen that the primary CSPs or the ordinary CSPs handle the constraints as a rigid. That is, every solution obtained should satisfy all the constraints at the same time. If there are constraints associated with any of the states or goal, it should satisfy all the constraints. They are called as normal CSPs, and we treat these constraints as rigid. They are said to be non-flexible because if any of the constraints are not satisfied, it is treated as violated. The rules are being violated. Now we have another form of CSP which is called as changeable CSP or flexible CSPs, where we have the provision to relax some of the pre-assumptions made on these constraints. So we can have a relaxation on some of the constraints based on some priorities. We said to have a relaxation partially on the constraints and allow the solution not to comply with all of these constraints. Some of the constraints can be relaxed. Such CSPs are called as flexible CSP. There are different types of flexible CSPs. One is max CSP. Here, the violation of several constraints are permitted, and the quality of the solution depends on, or it is measured in terms of, the number of satisfied constraints. If there are X number of constraints, we are permitted to violate many of them, and the quality of the solution depends on the number of constraints that are being satisfied. Suppose there are 10 constraints for a solution or a problem, then we can solve this with following 8 of them or 4 of them or 3 of them, any value. Naturally, the best solution will be that one which is having the highest number of constraints satisfied. Then weighted CSP is another form of max CSP which comes under flexible CSP. Here, every constraint is evaluated based on some weights assigned. We are assigning predefined preference weights, and this will be taken into consideration for satisfying the constraints. Another one is fuzzy CSP. Here we consider a constant function based on the value of the variable, and this constant function runs from two extremes, runs from one extreme to the other extreme, and these extremes are completely satisfying the constraint, and the other extreme is completely violating the constraint, and this function runs from completely satisfied to completely violated form of constraints. And this problem works on this function. So here the satisfaction of a constraint is a constant function of its variable's value moving from completely satisfied to completely violated. Because in flexible CSP, we have the provision of violating constraint. It can be any number from 0 to the maximum number of constraints. And we can represent these numbers in the form of a function. And the solution working with this function which is a constant function based on the variable's value. We call it as fuzzy CSP. Now for creating or specifying the CSP, we follow these steps. We know that the components of a CSP are the triplet, which includes the set of variables and the domains for each of the variables, and finally the constraints. Creation of these three objects specifies a CSP. So the steps are: create the variable set, create domain for each of the variables which are declared in the variable set, and create the constraint set with variables and domains. So these are the three steps required for creating a CSP. And with these three steps, we have to find an optimal solution. Normally, depending on the method used for solving a problem, the constraints are normally expressed in terms of the relation between the variables. We have a variable set and the relation between those variables are expressed for solving a problem. Let us see some examples. Let us consider a notation like C means constraint on ijk, C of ijk, specifying values for the variable with these three options: v of I, v of j, and v of k. And these values for I, j, and k are permitted simultaneously. They can have some values at the same time. I'll explain this with an example. Consider two variables x and y, where x can take the values 1, 2, and 3, and y can take the value 2 and 3 at the same time. So the values of y does not depend on the values of x. So the domain of x is 1, 2, and 3, and the domain of y is 2 and 3. Now let us impose some constraints on this. The first constraint is x equal to y. What does it mean? Whenever we consider the values from this domain and from this domain, the values from this domain corresponds to values for x, and with this domain it corresponds to values of y. So whenever we take values from this and this for x and y respectively, we should follow this constraint, that x should be equal to y. So the expression, as we mentioned about C of I, j, k, can be represented here as C of x, y, because we are having only two variables, C of x, y, can take the values 2, 2 and 3, 3. Because 1 is not possible. Why? Because there is no value 1 corresponding to y. We should take only the values where x and y have the equal values. So 2, 2 and 3, 3 are the only possibilities available with this constraint. Now if we change the constraint to this form, when x is constraint where x is less than y, then C of x, y will be changed from this to this format. We can take two values for x and y such that always the value of y should be more than that of x according to this constraint. So we can have 1, 2, 1 is less than 2, 1, 3, again 1 is less than 3, and 2, 3. 2 is less than 3. We cannot take the value of 3 for x because y is not having a greater value which is higher than 3. Hope you are following me. Likewise, we can have multiple constraints working at the same time, and while imposing these constraints we will have different combination of cxy if we are taking two variables into account. Now, based on the number of variables being considered, we can have different types of constraints. If we are considering only single variable, then we call it as unary constraint. Suppose say we are considering only the variable x, and we are saying that the value of x can be anything except say 4 or 7. So x can take any value. It should not be equal to 4 or 7. So there we are considering only one variable, which is x. Similarly, we can have two variables, as in the previous example we have discussed, x and y. Then we call it as a binary constraint. We can have three variables at the same time. We call it as ternary constraint. Likewise, the number of variables being considered can be any number. So we can have k-ary constraint having a size of k variables. So this is a binary constraint representation of a problem. We are having the nodes of a graph are variables. We are having 5 variables here. They are being represented with two disjoint graphs because x2 and x4 doesn't have any connection with x1, x3 and xy. They are disjoint. So when we represent a problem in the form of a graph, their nodes represent the variables and the edges represent the constraints. The nodes are variables and edges are constraints, and the domain is the permitted values for each of the variables. We will be having separate domains for each of the variables. So here x1 and x3 have the constraint say 5, 7, 2, 2. What it means? When x3 takes the value 5, x1 can have the value 7. Or when x3 takes the value 2, x1 can take the value 2. Similarly, when x3 is having the value 3, x5 can take only the value 7. When x4 is having the value 1, x2 can be 3. When x4 is 2, x3 and x2 can be 4. When x4 is 7, x2 can be 6. And the constraint for x1 and x5 is not defined. So this is a representation of binary constraint because we are taking into account only two variables at a time for a constraint. Here we are taking only x1 and x3. Here we are taking only x3 and x5. And here it is x2 and x4. So only two variables are being considered for formulating the constraints.